good evening. Settle in, get comfortable, and prepare for a journey to the very edge of the observable universe. Imagine looking up at the night sky. For centuries, you've watched the same bright pinprick of light. It lives its life, shining, changing color slightly, but it's always there. And then one day, it just vanishes. It doesn't explode in a blinding flash. It doesn't slowly fade away. It simply disappears, as if someone flipped a cosmic switch. Sounds like science fiction, doesn't it? But this is exactly what actually happened. Today, I'm going to tell you the story of a star whose sudden disappearance baffled the entire global astronomical community. This is a story that challenged everything we thought we knew about the lives and deaths of massive stars. We'll dive into a cosmic detective story where the clues were gathered by humanity's most powerful telescopes, yet the solution turned out to be far stranger than anyone could have imagined. Prepare to hear about a mystery that may have given us our first glimpse behind the curtains of a black hole's birth. To grasp the scale of this puzzle, we have to travel immense distances. Our journey takes us to the constellation Cepheus, approximately 22 million light-years away from Earth. There resides an incredibly beautiful spiral galaxy known by its catalogue number, NGC 6946. Astronomers have given it a much more poetic name, the Fireworks Galaxy, and for good reason. This galaxy is a true cosmic star-making factory. It experiences supernova explosions roughly 10 times more frequently than our own Milky Way. This is why it remains under constant observation. Scientists are hoping to catch a star at the exact moment of its grand finale, the supernova explosion, and in 2007, one specific object captured their attention. It was a colossal star, a blue supergiant, roughly 25 times the mass of our Sun. It was bright, hot, and by all indications nearing the final stage of its evolution. They designated it N6946-BH1. Scientists were certain they were about to witness a magnificent cosmic spectacle. They waited for an explosion that would briefly outshine the light of millions of other stars in the galaxy. But what happened next defied every existing theory. So, the story begins back in 2007. A team of astronomers led by Christopher Kokenek at Ohio State University was conducting a systematic survey of the Pinwheel Galaxy, also known as NGC 6946. Their main goal was simple: the hunt for supernovae. Using the Large Binocular Telescope, or LBT, located in Arizona, they scanned the galaxy looking for stars that suddenly increased their brightness, a telltale sign of an imminent stellar collapse. And that's when one star caught their attention. It would later be designated N6946-BH1. On earlier archival images, it had been just another faint dot among millions. But in 2009, something truly strange happened. The star began to rapidly increase its luminosity. Within months, it was glowing more than 1 million times brighter than our own Sun. For the astronomers, this was both a major red flag and an incredible stroke of observational luck. They hypothesized they were witnessing what is known as the star's death throes. This behavior is typical of extremely massive, unstable stars that aggressively shed their outer layers right before their final cataclysmic collapse. It's a process similar to a volcano rumbling and spitting ash before the powerful main eruption. The scientists were thrilled. They immediately pointed every available instrument, including the powerful Hubble Space Telescope, at the star to record every detail of this rare event. They fully expected that this short, violent surge of brightness would be followed by a colossal supernova explosion that could be studied for decades. The entire scientific community held its breath, awaiting the spectacular finale of this cosmic drama. unfolding 22 million light-years away. Let's take a closer look at what this star actually was. It belonged to the blue supergiant class. These are among the hottest, brightest, and most massive stars in the entire universe. Their lives are brief and violent. While our Sun is expected to last for about 10 billion years, the lifespan of such a supergiant is only a few million years. They burn through their nuclear fuel at a truly astonishing rate. This particular star was estimated to be roughly 25 times more massive than the Sun. Picture a ball of scorching plasma so vast that it could easily contain millions of Earth-like planets. The surface temperature reached tens of thousands of degrees Celsius, which gave it that characteristic blue-white hue. The flare-up recorded back in 2009 was essentially a giant eruption of matter. The star had literally shed part of its outer layers into the surrounding space. This phenomenon wasn't entirely unique. Astronomers already knew of other examples of so-called imposter stars or fake supernovae. The most famous case is Eta Carinae, located in our own galaxy, which experienced a similar cataclysm in the 19th century. Typically, after such an ejection, the star calms down. Its brightness dims, but it continues to exist, preparing for its next, perhaps final, act. And this was exactly the scenario scientists expected from N694-6-BH1. They maintained their observations, assuming the star had simply blown off steam and would now return to its normal state before eventually exploding. But it had a monumental surprise in store for them, one that completely upended their understanding of stellar evolution. No one could have predicted that this wasn't the beginning of the end, but the end itself. The observations continued. Years went by. Astronomers waited patiently. 2010, 2011, 2012. Following its massive flare-up in 2009, the star began its slow decline. This fit the existing theory perfectly. The ejected shell of gas and dust was expanding and cooling, and the object's brightness was steadily dropping. Everything was proceeding as planned. Scientists meticulously analyzed the star's light spectrum to determine the chemical composition and expansion rate of the ejected material. This data was invaluable for building models of the pre-supernova state of massive stars. Every new image, whether from the Hubble Space Telescope or the LBT, added crucial details to the overall picture. It looked like a textbook case, one that would be cited for decades as the most thoroughly documented example of a star's preparation for a supernova. Kochanek's team, along with research groups worldwide, were certain that eventually, be it a year, a decade, or a century from now, that spot would erupt in a brilliant final flash. But in 2015, when they next focused their telescopes on that precise patch of sky, a shock awaited them. The star was simply gone. On the visible light images captured by Hubble, the spot where an object 1,000,000 times brighter than the Sun had recently shone was now empty, an absolute inky black void. The disappearance was so completely unexpected that the scientists' first reaction was outright disbelief. They triple-checked the coordinates, the telescope settings, and cross-referenced the new images with the old data. There was no mistake. The star they had been so meticulously monitoring had simply vanished. Imagine the shock the astronomers must have felt. It was like watching a lighthouse on a distant shore, seeing its powerful beam flash brightly, and then, the very next instant, finding absolutely nothing there, not even rubble. Where could an entire star, 25 times the mass of our Sun, possibly have gone? The first thought that sprang to mind was simple. Maybe it did go supernova and we just missed the initial blast. That's entirely plausible. The peak brightness of a supernova only lasts a matter of days or weeks. If the weather was poor or the telescopes were focused on other targets during that window, the flash could easily have been overlooked. But this hypothesis quickly failed to stand up to scrutiny. A supernova explosion of that magnitude is not the kind of event that simply disappears without a trace. It leaves behind an expanding cloud of superheated gas known as a supernova remnant. This remnant glows for thousands of years across the entire electromagnetic spectrum, from radio waves all the way up to X-rays. Furthermore, at the core of that cloud, there must be a superdense remnant, either a neutron star or a black hole. The astronomers meticulously scoured that region of the sky using every available means. They looked for radio signals from a pulsar, X-ray emission, from an accretion disk, any evidence whatsoever of a recent cataclysm. But they found nothing. Absolutely zero. It was now perfectly clear a classic supernova explosion had not taken place here. The mystery only deepened. The star hadn't exploded, yet it had vanished. Where on Earth, or rather, where in the universe, had it gone? So the hypothesis about the missing supernova was out. They needed to find another explanation. The next idea scientists began to test was more mundane perhaps, but perfectly logical. What if the star hadn't vanished at all, but was just hiding? We know that during its outburst back in 2009, it expelled a tremendous amount of material. Perhaps this material condensed into a dense cloud of dust, completely obscuring the star from our view. It's like hanging a thick blanket right in front of a bright lamp. The bulb is still shining, but we can't see it. This theory seemed quite plausible. Cosmic dust is incredibly efficient at absorbing visible light. If a sufficiently thick veil of dust had formed around the star, then the Hubble Space Telescope, which primarily operates in the visible and ultraviolet light spectrums, would indeed be unable to detect it anymore. However, this hypothesis had one major vulnerability, one they could easily test. That's because when dust absorbs the star's light, it heats up and begins to glow itself, radiating in the infrared range. This is known as thermal emission. Therefore, if the star was still there, hidden behind the dust cloud, we should have seen a bright source of infrared light right where it used to be. Scientists turned to data from the Spitzer Space Telescope, which was specifically designed for infrared observations. They focused Spitzer on the exact location where the star once shone and began analyzing the resulting images. And what they found only deepened the mystery. The observations from the Spitzer Space Telescope delivered baffling results. They did detect an infrared source at the location of the vanished star. It seemed initially that the mystery was solved. The star had simply been hidden behind a cloud of dust. But the situation was far more complicated than that. When astronomers analyzed the brightness of this infrared source, they realized it was far too faint. Much dimmer than it should have been if a blue supergiant, still burning brightly, was merely concealed by a curtain of dust. The energy emitted in the infrared spectrum was nowhere near enough to account for a star with the mass of 25 suns. It was like expecting the glare of a powerful searchlight behind a heavy curtain, only to find the weak flicker of a candle instead. This meant the hypothesis of an obscuring dust cloud in its purest form simply didn't work. Yes, there might have been some dust there, perhaps remnants from the 2009 flare-up, but the star itself, at least in its previous magnificent state, was not behind it. The scientific community found itself at an impasse. All standard explanations had failed. The star had not exploded, and it hadn't just hidden itself. It had genuinely vanished, leaving behind only a faint, fading thermal echo. A completely new, revolutionary idea was needed, and that idea was eventually found. It had been predicted by theorists decades ago, but until this moment it had lacked any observational confirmation. This was the concept of the failed supernova. So what exactly is a failed supernova? To grasp this concept, let's first review how a typical supernova explosion occurs. Throughout a massive star's life, thermonuclear fusion reactions take place in its core. First, hydrogen fuses into helium, then helium into carbon, and so on, until an iron core forms right at the center. Iron is the final product of stellar nucleosynthesis. When iron fuses, it doesn't release energy, instead, it absorbs it. At this point, the thermonuclear furnace in the star's center shuts down. Gravity, which was previously balanced by the outward radiation pressure from the core, finally takes over. The core begins to rapidly compress under its own weight, a process known as gravitational collapse. This happens in a fraction of a second. The star's outer layers rush toward the center at speeds approaching 1/4 the speed of light. When these layers strike the superdense compressed core, an incredibly powerful shock wave is generated. This wave, bolstered by a torrent of neutrinos streaming from the core, blasts outward, tearing the star apart in a truly spectacular explosion. This is a Type II supernova. We observe a brilliant flash of light, and what remains of the star is either a neutron star or, if the mass was extremely large, a black hole. But what happens if that shock wave isn't powerful enough to completely destroy the star? What if gravity wins utterly and decisively? This, in essence, is the core hypothesis behind the failed supernova. The failed supernova theory posits that under certain specific conditions, particularly in extremely massive stars, the shock wave intended to trigger the explosion is simply too weak. It forms and starts moving outward, but fails to overcome the colossal gravitational pull exerted by the star's outer layers. Instead of blowing the star apart, the wave stalls, dissipates, and crashes back onto the core. This is where something astonishing occurs. With the failed shock wave, nothing remains to halt the subsequent gravitational collapse. The star's entire mass, all its outer envelopes that should have been ejected into space, plunges inward, falling directly beneath its own event horizon. The star collapses directly into a black hole, completely bypassing the bright supernova stage. To an outside observer, the result is exactly what astronomers observed. A star that was visible one moment simply vanishes the next. It doesn't explode, it implodes. This process is not entirely silent, however. As matter collapses onto the forming black hole, an immense amount of energy must be released. But this energy isn't light, it's released as neutrinos, tiny, nearly massless particles that interact extremely weakly with ordinary matter. Furthermore, just before disappearing, the star is expected to shed a small fraction of its outer envelope, a sort of dying gasp. This entire scenario matched the observations made by astronomers regarding N6946-BH1 with stunning accuracy. Let's quickly compare the observed facts with the theory of the failed supernova. First, we were dealing with an extremely massive star, roughly 25 times the mass of the Sun. Theory specifically predicts that giants of this scale are capable of a direct collapse into a black hole. Less massive stars, in contrast, are expected to explode as standard supernovae. Second, in 2009, we observed a powerful outburst as the star shed part of its outer layers. This event can be interpreted as the star's death throe, preceding the final collapse. It was essentially the star purging excess mass before vanishing into oblivion. Third, following the outburst, the star completely disappeared from the visible spectrum. This perfectly matches a scenario where all of the star's material fell beneath the black hole's event horizon. Fourth, we detected neither the bright flash of a supernova nor a nebula remnant. This is the crucial evidence against a classic stellar explosion. Fifth, and most crucially, a faint infrared source remained exactly where the star once was. What accounted for this residual emission? According to the failed supernova model, the material ejected in 2009 continued to expand and cool. Furthermore, a small portion of the matter spiraling into the nascent black hole may have formed a tiny, hot accretion disk, which would also emit strongly in the infrared. Over time, this source was expected to grow fainter and cooler, shifting its radiation into longer radio wavelengths. Subsequent observations confirmed precisely this. The infrared source gradually faded away. All the evidence converged. It appeared that astronomers had, for the first time in history, witnessed the birth of a black hole. If definitively confirmed, this discovery holds colossal implications for our understanding of the universe. For starters, it neatly solves a long-standing cosmological riddle known as the missing supernova problem. Theoretical models predict we should be seeing far more massive star explosions, supernovae, than current observations actually show. For years, astronomers have been scratching their heads, wondering where these expected stars vanish. The failed supernova hypothesis offers an elegant solution. A significant fraction of these massive stars, perhaps up to 30% of them, don't explode. Instead, they quietly collapse directly into black holes. They simply vanish from the sky, never putting on the expected farewell fireworks show. This means the universe could be absolutely teeming with stellar mass black holes, far exceeding our previous estimates. These invisible objects drift through galaxies, their existence completely hidden until they happen to reveal themselves, perhaps by gravitationally tearing apart a nearby star. The case of N694 6-BH1 provides the first direct observational evidence of this specific process. It opens up an entirely new window into studying the most extreme phenomena in the cosmos. We can no longer view the death of massive stars as a single scenario event, culminating in a brilliant explosion. It turns out they have an alternative, far quieter and more mysterious path, a silent plunge into oblivion. Let's take a slight detour and talk about the incredible instruments that made this amazing discovery possible. The main characters in this story, besides the star itself, are two key telescopes, the Large Binocular Telescope, LBT, and the Hubble Space Telescope. The LBT, located on Mount Graham in Arizona, stands as one of the most powerful ground-based optical telescopes in the world. Its unique feature is its configuration. It uses two massive mirrors, each measuring 8.4 meters in diameter, mounted together on a single structure. Working in tandem, they achieve the resolving power of a single 23-meter telescope. It was thanks to the LBT's wide field of view and high sensitivity that astronomers were able to monitor the fireworks galaxy and spot the star's initial flash. However, ground-based telescopes face one major drawback: the Earth's atmosphere. It distorts images, introduces interference, and blocks certain types of radiation. To get the clearest possible picture and truly peer into the deepest corners of the cosmos, you need a telescope placed outside the atmosphere. And this is where the legendary Hubble enters the scene. Launched in 1990, it has been giving us breathtaking views of the universe for over 30 years. Its main mirror, measuring 2.4 meters in diameter, might seem modest compared to the giants on Earth. But because it operates without atmospheric distortion, it provides unparalleled image clarity. Crucially, it was the data from Hubble that allowed scientists to state with absolute certainty, in visible light, the star had truly vanished. The role of the Hubble Space Telescope in this research cannot be overstated. It was its sharp, discerning eye that allowed us to truly separate the signal from the noise. The galaxy NGC 6946 is extremely distant, and in images taken by ground-based telescopes, the individual stars within it blur together, into an indistinct, smeared mess. Resolving a single star, let alone monitoring its changes over time, is no easy feat. However, thanks to its unique vantage point in space, Hubble was able to provide the necessary resolution to isolate our target star from hundreds of its neighbors. The crucial evidence came from comparing Hubble images, those taken before 2009 during the star's sudden brightening, and those taken after 2015. In the first set of images, we see a faint point of light, in the second, a bright star, and in the third, nothing but an absence. This iconic sequence of images became the cornerstone for proponents of the failed supernova theory. But the telescope's work didn't stop there. Once the star vanished in visible light, the key role shifted to the already mentioned Spitzer Space Telescope and later other infrared observatories. These instruments allowed scientists to study the faint afterglow that remained at the collapse site. By analyzing the spectrum of this infrared radiation, researchers could estimate its temperature and confirm that the emission originated from an expanding cloud of dust, rather than from a hidden, obscured star. This entire story is a perfect illustration of how modern astronomy operates, by leveraging the unique strengths of various instruments. Ground-based telescopes perform wide-scale surveys and locate interesting targets, while space observatories conduct the crucial deep dives, allowing us to peer into the very essence of these cosmic phenomena. Now let's circle back to the core concept of the black hole itself. What exactly is this object that our massive star presumably turned into? According to Einstein's general theory of relativity, a black hole is a region of space-time where the gravitational pull is so immense that nothing, not even light itself, can escape, regardless of how fast it's moving. The boundary of this region is known as the event horizon. Anything crossing the event horizon from the outside is immediately doomed to spiral inward toward the black hole's center, the singularity, a point of infinite density. We can't actually see a black hole directly because it emits no light. We can only infer its existence through indirect signs, either by observing its gravitational influence on surrounding objects or by detecting the radiation emitted by matter falling into it. In the case of S6946-BH1, we may be witnessing the second effect in action. The faint infrared glow could be caused by leftover material that hasn't immediately fallen in. Instead, it formed a temporary accretion disk swirling around the black hole. Friction within this disk heats the matter up to extreme temperatures, causing it to begin radiating light. As this material is gradually consumed by the black hole, the luminosity should fade, which is exactly what we are observing. If confirmed, this gives us a unique opportunity to study the feeding process of a nascent black hole. This provides invaluable insight into how these mysterious objects interact with their environment in the very first moments of their existence. It's crucial to remember that while the failed supernova hypothesis is currently the leading explanation for the star's disappearance, it remains just that, a hypothesis. Science is a process, not a collection of final truths. There is always a possibility that we are missing a critical piece of the puzzle, and that an alternative, even more exotic, explanation exists. What might these alternatives be? One possibility, however unlikely, is that we witnessed a completely new, previously unknown type of stellar variability. Perhaps the star didn't vanish, but instead transitioned into an extremely faint and long-lived state that our current understanding of physics cannot yet explain. Another, even more fantastic idea involves the so-called Thorne-Zhitkov objects. This is a hypothetical class of stars consisting of a red giant, or supergiant, with a neutron star, rather than a normal stellar core sitting at its center. These objects can be unstable and might eventually collapse without producing a bright flare or supernova explosion. However, the observed characteristics of N6946-BH1 don't fit this specific model very well. For now, the failed supernova remains the simplest and most logical explanation, one that is consistent with all the available data. Scientists continue to monitor this region of the sky, hoping to gather new data that will either definitively confirm this theory or force us to pursue new, even bolder ideas. Let's try to visualize this process on a massive scale. Imagine a star 25 times the mass of our Sun collapsing into an object where the radius of the event horizon is just about 75 kilometers. Picture that entire mass, 25 suns, crushed down into a sphere the size of a small city. The density and gravity near such an object reach unimaginable extremes. For an observer falling into the black hole, time slows down. Yet for an external observer, time appears to stop completely at the event horizon. This collapse, which takes fractions of a second for the star itself, is stretched out into eternity from our perspective. We will never actually see the final atom of matter cross the event horizon. Instead, we would only see that atom's image freeze and redshift until it eventually fades from view entirely. This is one of the most astonishing paradoxes of general relativity. The disappearance of NGC 6946-BH1 isn't just an astronomical curiosity, it is a direct demonstration of fundamental laws of physics operating at their most extreme limits. It confirms that Einstein's boldest predictions, made over a century ago, hold true in the real universe. By studying events like this, we aren't just learning more about stars, we are fundamentally testing the very foundation of our cosmic reality, looking into realms where our everyday concepts of space, time, and matter cease to have meaning. One question this event raises concerns the fate of heavy elements. We traditionally thought that all elements heavier than iron, the very material that makes up us and our planet, are forged exclusively in supernova explosions. During these blasts, extreme temperatures and pressures allow atomic nuclei to capture neutrons, transforming them into gold, platinum, uranium, and other heavy elements. These elements then scatter throughout the galaxy, becoming the building material for new stars and planets. But if a significant fraction of massive stars don't explode, but instead collapse directly into black holes, how does that impact the universe's chemical evolution? It means that all the heavy elements synthesized deep inside those stars are permanently trapped beyond the black hole's event horizon. They will never reach the interstellar medium and cannot participate in the formation of new generations of stars. This suggests that existing models of galactic chemical evolution may need to be fundamentally revised. It's possible that the contribution of supernovae to enriching the universe with heavy elements has been significantly overestimated. Astronomers will have to look for alternative sources, such as the mergers of neutron stars, which, as recent observations show, are also powerful factories for producing gold and platinum. Thus, a single observation of a vanishing star triggers an entire chain reaction of re-evaluation across diverse fields of astrophysics. It's like finding one strange rock that forces geologists to completely rethink the formation history of an entire mountain range. Let's return to the chronology of events and reconstruct the timeline with maximum precision so you can truly appreciate the drama of this discovery. Prior to 2001, archival images show a clear, stable star right where our object is now located. It existed, it was fixed, it was stable. From 2001 to 2009, however, it starts showing signs of instability. Its brightness begins to fluctuate wildly. These are the first warning signs of the coming storm. Then in 2009, a massive outburst occurs. The star's luminosity spikes, increasing its brightness by 1,000,000 times that of the Sun. This peak explosion lasts for nearly 300 days. Scientists record this colossal event and initiate intense, dedicated observation. From 2010 to 2014, the star slowly begins to fade. Its brightness in the visible spectrum gradually drops. Everything seems to be following the classic scenario of a fake or failed supernova. Nothing appears out of the ordinary. 2015. New observations taken by the Hubble Space Telescope reveal that in the visible spectrum there is nothing left where the star used to be. Simultaneously, however, the Spitzer telescope detects a faint infrared source at that exact location. This is the precise moment the mystery is born. In 2016, 2017, and in the years that followed, astronomers published their results. The prevailing hypothesis proposed a failed supernova. Subsequent infrared observations showed that the residual source continued to dim, which perfectly aligns with the theoretical model. This clear, documented sequence of events makes the case of N6946-BH1 truly unique. It wasn't merely a one-off observation, it was a full, recorded history, written in the light that traveled millions of years to reach us. What happens next with this object? Observations will certainly continue. Astronomers will monitor the fading of the infrared source. Eventually it should vanish completely, even in this band. Perhaps in a few years or decades, we might attempt to detect radio emissions from the remaining material accreting onto the black hole. But the most exciting developments might await us in the future with the advent of next-generation telescopes. For instance, the James Webb Space Telescope, with its unparalleled infrared sensitivity, will be able to study the leftover dust cloud in incredible detail. It can analyze its chemical composition and dynamics, providing new clues to understanding exactly what happened to the star in the final moments of its life. And in the even more distant future, perhaps we will be able to detect gravitational waves from similar events. Current detectors like LIGO and Virgo are capable of registering the mergers of black holes and neutron stars. However, the gravitational wave signal from the collapse of a single star is much weaker. But with technological advancement, it is certainly possible that our descendants will be able to hear the birth of black holes across the universe by registering the ripples in space-time they create. And then the story of N6946-BH1 will transform from a unique case into one of many, confirmed by an entirely new observation method. So, this story is far from over. We are only standing at its very beginning. Let's take a moment to reflect on the philosophical significance of this event. We are used to imagining the death of a star as something majestic and brilliant. A supernova explosion is a cosmic salute, marking the giant's demise while simultaneously giving birth to new life. It scatters elements throughout space, the building blocks for future stars and planets. This is the ultimate cycle of creation and destruction. But the failed supernova offers a starkly different scenario. It is death without resurrection. It is a quiet retreat into absolute oblivion without fanfare or lasting legacy. Everything the star accumulated over millions of years, all its synthesized elements, its colossal energy, is instantly and eternally locked behind the event horizon. From the universe's perspective, this is an act of pure, clean disappearance. This makes us realize just how diverse and unpredictable the evolutionary paths in the cosmos truly are. There is no single script for everything. Alongside the bright and obvious processes, there are always quiet and hidden ones that may play an equally critical role in the larger cosmic picture. This reminds us how little we actually know. Every new discovery like this one doesn't so much give us answers as it raises new, even deeper questions. And that is the core beauty of science, the infinite journey towards the horizon of knowledge, which, much like a black hole's event horizon, remains forever unattainable, yet perpetually alluring. Interestingly, the fireworks galaxy itself, the stage for this stellar drama, is a focus of intense scrutiny, and not just because of its frequent supernovae. It's known as a starburst galaxy, meaning new stars are forming there at an immense rate, especially within its spiral arms. It is a highly active, vibrant galaxy. And in environments like this, where so many massive stars are being born, we should naturally anticipate a large number of stellar deaths, both the spectacular bright ones and the quiet, hidden ones. Perhaps NGC 6946-BH1 is just the tip of the iceberg. How many similar disappearances have occurred in this and other galaxies that we simply missed because we weren't monitoring a specific star before and after the event? After all, detecting such a disappearance requires high-resolution archival images, followed by painstaking, repeated observations several years later. This demands enormous resources and patience. The project that led to this discovery was specifically designed for systematic monitoring, and its success clearly demonstrates just how vital these long-term observational programs are. They allow us to view the universe not as a static photograph, but as a dynamic, constantly changing movie full of unexpected plot twists. And who knows what other surprises active galaxies like the fireworks galaxy are holding for us. Perhaps you're wondering, could this kind of event happen to our Sun? Could we wake up one morning and find it missing from the sky? Let me reassure you immediately, no, it cannot. Our Sun is a dwarf star. Its mass is simply too small to end its life in a spectacular supernova explosion or collapse into a black hole. The Sun's fate is far more tranquil and predictable. In about 5 billion years, it will run out of hydrogen fuel in its core and begin to swell, transforming into a red giant. Its outer layers will expand so far that they will engulf Mercury, Venus, and perhaps even the Earth. Following this phase, the Sun will shed its outer shells, creating a beautiful planetary nebula. What will remain at the center is its former core, a small but extremely hot and dense white dwarf. This white dwarf will slowly cool over trillions of years, gradually fading into a cold, dark object known as a black dwarf. So, rest assured, our Sun won't suddenly vanish. Its demise will be a very slow and gradual process. Dramatic finales involving a black hole collapse are reserved only for the most massive stars in the universe, those that live fast and die young. Their mass must be at least 8 to 10 times greater than the mass of our Sun, and for a failed supernova, the requirement is likely even higher, in excess of 20 solar masses. Let's talk about the name of the object, NGC 6946-B1. What exactly does it mean? NGC 6946, as we know, is the galaxy's catalogue number from the new General Catalogue of Nebulae and Star Clusters. But the abbreviation BH1 stands for Black Hole Candidate 1. This name was assigned only after scientists hypothesized that the star had undergone a collapse. The name reflects its unique status. This is highly likely the first newborn black hole in history, whose creation was directly witnessed as the disappearance of its progenitor star. In many ways, the name itself is a monument to this discovery. Of course, until we get irrefutable proof, it will remain a candidate. But it is an extremely strong candidate. It is often the case in science that new classes of objects are named after the first member discovered. Perhaps in the future, astronomers will speak of BH1 type objects, referring to stars that ended their lives through direct collapse. And everyone will know that the precedent was set by this mysterious event in the fireworks galaxy, an event that forced us to rewrite a chapter in astrophysics textbooks. It's crucial to point out that this discovery was only possible thanks to massive collaboration between scientists and observatories worldwide. This wasn't the work of one person. Christopher Kochonek's team, responsible for the initial find, comprised dozens of researchers spanning multiple nations. They relied on data not just from the LBT and Hubble telescopes, but also from numerous other ground-based and space observatories. Crucially, their findings were then independently verified and cross-referenced by other scientific groups. This is precisely how modern science operates. Breakthroughs happen at the intersection of diverse expertise, fueled by data sharing and vigorous, often heated, discussions. One scientist might specialize in observation, another in theoretical modeling, and yet another in data analysis. Only by combining these specialized efforts can they piece together a coherent, complete picture from isolated fragments. The story of the vanished star is a perfect illustration of the international scientific community's ability to work together and unravel the most complex mysteries the universe throws our way. This is a triumph not just of technology, but of human intellect and our innate capacity for global cooperation. Every single image captured, every line of code written, every scientific paper published on this subject, they are all small steps bringing us closer to understanding our place in this vast and astonishing cosmos. Can we find other missing stars like this? Absolutely. Now that astronomers know exactly what to look for, projects dedicated to analyzing archival data are popping up all over the world. Scientists are comparing old and new sky surveys looking for stars that appear in older images but are completely missing from recent ones. This is meticulous, painstaking work, akin to finding a needle in a cosmic haystack. The universe is vast, and the number of stars captured in these photographs runs into the billions. Most of these disappearances will turn out to be false alarms, defects on photographic plates, variable stars that are simply at their brightness minimum, or errors in the catalogues themselves. But hidden among them could be genuine new candidates for failed supernovae. Every single new object discovered would be invaluable. It would allow us to test whether the case of N6946-BH1 is unique, or if this is actually a common phenomenon. We could then gather statistics. How often does this occur? Does the probability of direct collapse depend on the star's mass, its chemical composition, or its environment? The answers to these questions will allow us to build far more accurate and complete models of stellar evolution, so it's very possible we'll be hearing about several more of these cosmic detective stories in the coming years. Let's get back to the underlying physics. What happens to matter when it falls into a black hole? According to classical theory, matter is ripped apart by immense tidal forces. Imagine an astronaut falling feet first. The gravitational pull on their feet would be vastly stronger than the pull on their head. This difference in force would stretch their body like spaghetti. This process is aptly named spaghettification. Eventually, all that matter is reduced to a stream of elementary particles which cross the event horizon and rush toward the singularity. What happens inside the singularity itself is a mystery. General relativity breaks down at this point. We need a new theory that unites gravity and quantum mechanics, what we call the theory of quantum gravity. It's possible that the center of the black hole doesn't contain infinite density at all, but instead holds something entirely different, something we cannot yet even conceive of. Some theories hypothesize that matter falling into a black hole might re-emerge somewhere in another universe through a so-called wormhole. Of course, these are currently just hypotheses bordering on science fiction, but by studying objects like the newborn black hole in the fireworks galaxy, we are gathering data that may eventually help our descendants create that ultimate theory of everything and answer the most fundamental questions about the nature of reality. One of the most intriguing aspects of this entire story is the burst of neutrinos. As I mentioned, an enormous number of these particles must be emitted during the core collapse and subsequent black hole formation. Neutrinos are known as ghostly particles. They have almost no mass and barely interact with ordinary matter at all. Every single second, trillions of neutrinos from the sun zip right through your body, and you don't even notice. To catch a neutrino, we need gigantic detectors buried deep underground or submerged underwater, shielding them from other cosmic rays. When the star N6946-BH1 collapsed, it should have produced a powerful yet very brief burst of neutrinos. Unfortunately, we most likely failed to detect this burst back in 2015. Firstly, the distance, 22 million light-years, is immense. By the time the neutrino flux reached Earth, it would have been extremely weak. Secondly, our current detectors may not have been sensitive enough to pick out that specific signal amid the general background noise. But this is a challenge for the future. If we can figure out how to reliably record neutrino bursts from events like this, it will provide us with an entirely new way to study the cosmos. We would be able to see processes hidden deep within the stellar core, completely inaccessible to traditional telescopes. This would be a genuine revolution in astronomy, a breakthrough comparable to the invention of the telescope itself or the discovery of gravitational waves. Consider this. The light we are seeing from that star has been traveling for 22 million years. The event we observed back in 2015 actually took place 22 million years ago. Back then, our earliest human ancestors were only just beginning to emerge on Earth, and the continents were configured entirely differently. While that light journeyed through intergalactic space, our planet went through multiple ice ages. Human civilization rose and flourished. We invented the wheel, built the pyramids, unlocked the laws of physics, and finally created the telescopes capable of capturing those ancient photons. And that is truly astounding. Astronomy is a time machine. It allows us to look directly into the past and bear witness to events that occurred long before we ever existed. The demise of that distant star is a message from the deep past, one that has only just reached us now to tell us something vital and new about the fundamental laws governing the universe. And who knows how many more such messages are currently speeding toward us from the furthest reaches of the cosmos, carrying the solutions to other great mysteries? All we can do is wait and watch the sky intently. Let's visualize this whole process. Imagine a massive, throbbing blue star right before us. Its surface is a cauldron of boiling plasma, constantly shedding torrents of superheated gas. Deep in its core, the final thermonuclear reactions are sputtering out. Suddenly the core contracts, the star convulses, shuddering like a living thing. A colossal shockwave of material blasts out into space. This is the blinding flash of the supernova we observe. But that flash is merely the prelude. The bulk of the star's mass now begins its swift, catastrophic collapse inward onto itself. Picture a gigantic waterfall, only the water is stellar matter, and the chasm below is a point at the center where gravity has become infinite. The star's outer layers vanish into this abyss, one after another. The radiant sphere of light rapidly shrinks, collapsing faster and faster until it implodes into a singularity and winks out. All that remains is an area of absolute blackness, powerfully warping the light of distant stars that happen to pass nearby. Orbiting this void is a faint, smouldering ring of debris, the last remnants of material violently ejected before the collapse. It glows softly in the infrared spectrum, like the cooling embers of a campfire. That weak glow is all that is left of a star that was once a magnificent celestial body, 25 times the mass of our own sun. It is a quiet, yet utterly magnificent spectacle, the birth of a light-devouring monster unfolding right before our eyes. What is the biggest lesson we can take away from this story? Perhaps it's that the universe is invariably more complex and fascinating than even our most ambitious theories allow. Every time we feel like we've almost grasped the whole picture, the universe throws us a new puzzle, one that forces us to radically rethink our assumptions. In the 19th century, scientists believed physics was nearly complete. Then came the theories of relativity and quantum mechanics, which completely turned that world on its head. Late in the 20th century, we thought we had a solid grasp on the life cycle of stars, but then came the case of N69446-BH1, which proved we were overlooking an entire class of cosmic phenomena. This teaches us two things: humility and curiosity. We must always be ready for the possibility that our most established knowledge might be incomplete or even outright incorrect. And we must constantly maintain that childlike curiosity that drives us to ask why and what if. It is this very curiosity that pushes science forward, moving from one solved mystery to the next, often leading to something even deeper and more profound. The story of the vanished star is the perfect testament to that. So let's quickly review the key evidence in this cosmic detective story. Exhibit A, a massive star, roughly 25 times the mass of our Sun, nearing the final stage of its life. Exhibit B, a powerful outburst recorded back in 2009, which astronomers initially mistook for a supernova precursor. Exhibit C, the complete disappearance of the star from the visible light spectrum by 2015. Exhibit D, the complete absence of any telltale signs of a supernova explosion, no residual nebula, no X-rays, and no radio emission. Exhibit E, the presence of a faint, fading infrared source precisely where the star used to be. The accused, gravity. The verdict: we are highly confident we witnessed a failed supernova, the direct gravitational collapse of a star into a black hole. This event doesn't just solve the puzzle of this one particular star, it sheds light on broader astrophysical mysteries such as the deficit of observed supernovae and the formation pathways for stellar mass black holes. This is a discovery that, without exaggeration, will be written into every future astronomy textbook. We are witnessing a new chapter in our understanding of the cosmos being written right before our eyes. And just like that, without a blinding flash or a grand explosion, the life of a giant star ended. It didn't illuminate its galaxy with a final brilliant light. Instead, it simply slipped into the shadows, leaving behind only a mystery and a newly formed black hole. This quiet demise has actually proven to be a far louder event for science than the most powerful supernova explosion. For the first time ever, we have direct evidence that stars have an alternative path into oblivion, not a fiery blaze but a shadowy fade. We were witnesses to the birth of an object from which not even light can escape, and the single most crucial and astonishing conclusion is that the universe might be teeming with countless such events. Perhaps right now, as you are listening to this, some distant star is just as quietly vanishing from the heavens, transforming into a black hole. The cosmos is filled not only with visible light but also with invisible darkness, and that darkness plays an equally critical role in its existence. The story of N69446-BH1 is a potent reminder that the most significant discoveries are often hidden not in the brightest light, but in the deepest shadows. Thank you for spending this time with me journeying through the depths of space. I hope this story was not only informative, but also brought you a sense of calm and peace. Please be sure to subscribe to the channel so you don't miss any new sleep lectures, and hit the like button on this video if you enjoyed it. Now I want to leave you with a question. What other universe-changing mysteries do you think are hidden from us? Secrets that could completely rewrite our textbooks? Share your thoughts in the comments below. Good night.